Example 8. The function f is defined by f of x is equal to the square root of 25 minus x squared from -5 to +5. So this function happens to be a square root function, or sorry, semicircle function. So it's the top half of a semicircle, and it's got a radius of 5. So this question asks for the derivative at x equals -3. So the first thing I'm going to do then is I'm going to find the derivative, f prime of x. When I differentiate this, I'm going to first of all differentiate the power. So 1/2 25 minus x squared to the power of -1/2. And then I'm going to apply the chain rule. So I'm going to times by -2x because there is an inside embedded function here that I need to apply chain rule to. So when I simplify this expression, I'm going to end up with the 2's canceling out. So I end up with -x on top. And in the denominator, I'm going to end up with the square root of 25 minus x squared. So there's my derivative. And then evaluating that derivative at -3, I'm going to plug -3 into here. So I get +3 over the square root of 25 minus 3 squared. This works out to be 3 over 25 minus 9 is 16. So I end up with 3 over 4 as my slope. Okay, so the second part of this says we have another function g that's defined partly by f from -5 to -3, and then from -3 to +5 is going to be defined by x plus 7. So I have my f part of this, that's the semicircle part, and then I have another part that's a linear function. Okay, so is it differentiable at x equals 3, at -3? So first of all, just have an idea what this looks like. We should kind of imagine this graph. This is a semicircle graph, okay, from -5 to -3. And then we have some linear function that's going to go have a slope of 1. Okay, and at this point to -3, we need to check for, first of all, continuity, and then we need to see if it's differentiable. We need to know that the slope is the same from left side and right side. So first thing is we're going to check for continuity. So we should check that the limit as x approaches -3 from the positive side, that's going to be x plus 7. That's going to be equal to 4. And then we need to check for the limit as x approaches -3 from the negative side. When we plug that into the semicircle function, the y value at -3 for square root 25 minus x squared. When we plug -3 in there, we get 4 as well. So we know that this is continuous. So here, this together, we can conclude continuity. So this is, first of all, continuous. Okay, so now, although the function is continuous, we don't know that the slope is continuous, or in other words, differentiable at that point. So what we're going to have to do is we're going to have to check the slope. So we're going to check the slope from the right-hand side, and the left-hand side. So I'm going to draw this in red here. From that side, it's the left side. So I'm going to check to see that the limit as x approaches -3 from the left-hand side, we want to check that g prime of x, we want to find what that's equal to. So when we do that, we're going to plug that into f prime, and at -3, we've already established that the slope is going to be +3 over 4. Okay, so that's the slope that we got from this portion here. Okay, that's the slope that we established here. So then we need to calculate the slope from the other side. So the limit as x approaches negative 3 from the positive side, g prime, well, since it's a linear function, we know that the slope here is 1. Okay, so slope is going to be equal to 1. And we can see that the slope from the left side and the right side do not equate. Okay, so we know that this is not differentiable. So the derivative is discontinuous. Okay, therefore, g is not differentiable. Okay, so g is continuous through negative 3, but there's a kink there because when it transitions from the curved function to the straight function, the slopes do not match. So it is not differentiable at that point. The last part of this is we want to evaluate this definite integral. To do this, we can see that this is not a standard integral. We need to recognize that the derivative of this inside function will account for the outside portion. Okay, this outside portion here is going to be accounted for by the derivative of the inside. So we're going to let u equal negative x squared. In fact, let's let this be equal to 25 minus x squared because that constant is easily accounted for in the derivative. And the du becomes negative 2x times dx. Okay, so we only want the x dx, so we're just going to move that negative 2 to the other side. And we can replace the x dx with the du divided by 2. So when we rewrite this integral, we have to be careful because we're going to now change this to u. So we're going to say x is equal to 0, x is equal to 5. And we're going to replace the x dx with a negative 1/2 du. And inside the square root, we're going to put in our u. Okay, and this is why we need the x equals 0 and x equals 5, because our variables in terms of u, but our bounds are now in terms of x. So anti-differentiating this, we're going to end up with negative 1/2 u to the power 3 over 2. We're going to increase the power by 1, divide by 3 over 2, and then we're going to evaluate this integral from x equals 0 to x equals 5. Okay, I'm going to simplify this expression. This becomes, the 2's are going to cancel out, so I'm going to end up with, looks like negative 1/3. My u is going to be replaced by 25 minus x squared. And this is going to be evaluated from, I don't need the x equals anymore because now my variables are in terms of x. And then I'm going to work this out. So negative 1/3. 25 minus 25 is going to be 0, minus 25 minus 0 is 25. So this is going to be to the power 3 over 2. So this is going to be, it's going to end up being 25 to the power 3 over 2. I'm just going to write this out first. Okay, so the 25 to the power 3 over 2, since it's 25 is a perfect square, we're going to square root first and then cube it. So this works out to be the negatives canceling out, 125 over 3, and that's going to be units squared, as that's going to be some area under this curve.